Good morning, everyone. I hope that you guys are enjoying your Monday morning. I hope that you're having a good start to your week. Um, just a second. Plug in my wallet. Oh, and then I want to go ahead and get started on our lesson. So what we talked about to kind of wrap up last week, or the conclusion of last week, was we were talking about the periodic table. And specifically, we were looking at different elements on the periodic table, and we were looking at the subatomic particles of, well, not only a set number of elements, but basically every element. Now, today, what we're going to go into is a little bit more detail about that. What we're going to talk about is not only the structure of an atom, but kind of the geography of an atom as well. And what I mean by that is we'll talk about the subatomic particles, which we've already discussed, but then we'll place those subatomic particles. Now, with that said, a couple of announcements. We have exam number 1 week from tomorrow. That will be administered in person and but it will also be administered online. Um, and I'm going to add this online exams, or I'll say online examiners must contact me. I'm not going to really put a hard deadline on that, but I will add the sooner the better. My thought process on the sooner the better is, well, if you contact me today, I can add you to the roster and then you can kind of avoid any sort of hangups there. Um, I'm also not going to put a deadline on it because, say a week from tomorrow morning at 9 a.m. or 8 a.m., you're prepared to drive from, say, Houston to San Marcos and your car breaks down. Well, first of all, I wouldn't want to leave Houston at 8 a.m. to drive to San Marcos to arrive at 10 a.m. But, if something were to happen Tuesday morning and you're like, oh my gosh, but I didn't send the email by Thursday at 3 p.m. Oh my gosh, I missed the deadline. Um, the only hang up there is going to be that it's just going to take a little bit longer. And I mean, barring or in the event that something like that happens and you contact me Tuesday morning at 8 a.m. and you say, hey, is there any possibility that I can take my exam online? My answer is going to, here's why. My answer is going to be sure thing. We can do that. But if I don't see that email until 10:25, I can't magically go back to 10 a.m. and give you the full amount of time or the exact start time. I'll talk more about the exam this upcoming Friday and next Monday. It is written, the practice exam is up. The exam will be 30 questions, and you'll have 1 hour to complete it. And those questions are multiple choice. Could I get folks to add to the chat a letter if you understand and a number if you don't understand or you have a question? Awesome. Okay, wonderful. So if anything comes up over the course of this week, let me know. I'll have office hours again tomorrow at 9 a.m. I'll say OH 9 a.m. Tuesday. And then after class is done today, because we always have a little bit of extra time, I'll be available to answer any questions that you have. Just hang around after class. So those are kind of the bookkeeping things that I wanted to mention. Oh, one last bookkeeping thing is that quiz number 2 goes live today and is due at 11:59 p.m. Multiple choice. In the event that you miss a quiz or you don't do as well as you wanted to on a quiz, just keep in mind that we have one drop. Everyone gets one dropped quiz grade. So, I'm just saying that kind of as a not really warning, but just a reminder. Like if you contact me and say, "Hey, can you open this quiz again?" or something like that. I'm not typically I don't like to respond with like, "Nope, too late, read the syllabus." Um, but I'll say, "No, I'm sorry, everyone has a drop." So just make sure that you don't have any large number of quizzes that are problematic, and you'll be in good shape. In addition to that, I've already tossed out some extra credit. I like to toss out extra credit. So with that in mind, though, an atom, that's what we're talking about today. We're talking about the atomic structure or structure of an atom, and we're talking about electrons within the atom right off the bat. Now, initially, when it came to understanding what an atom was, I think there was kind of a consensus that an atom makes up everything. And that's the joke that my kids are right around the point where they're going to start enjoying it. And that is, why can't you trust an atom? Because they make up everything. So that's a classic joke. And there you go. Now, if we look on the left-hand side of the screen here, and then look at this middle there, okay. So on the left-hand side is this very rudimentary, detail-free idea of what an atom is. Okay, everything, this baseball card, for example, is made up of atoms. Okay, what are atoms? Well, they're small, circular, spherical things. They take up space. They've got protons, neutrons, and electrons. Now, early on, where are the protons, neutrons, and electrons? And the answer was, they are contained within the sphere. Then, as people were like, well, that's a cool non-idea. Let's see if we can get some more definition to that. There's this theory right here known as the plum pudding model of an atom. And so I've never had plum pudding. Um, Generally, I don't like pudding, so I'm not, and I'm not like a well-traveled person, so I wouldn't have, sought out plum pudding if I had ever been to England or anything like that. But my understanding is that plum pudding is pudding and it has plums in it. Now, the idea for this plum pudding model is that, well, basically the entirety of an atom has a positive charge. And then kind of randomly dispersed are electrons. So I would say that electrons are peppered throughout an atom. An atom. I think that a good comparison would be to say something like, oh, well, like boba tea, where if you drink boba tea, surprise, you might get tapioca or one of the balls. I have had boba tea one time in my life, and I thought it was really, really disgusting. I really did not like it because I guess my brain was like, you're drinking something, and if there's something in there, it better be ice and it better be crunchy. And instead, my mind was rewarded with this weird, like, soft piece of bubble gum. And I was like, oh my gosh, did I just did I just drink up a, is this like a really small water balloon? And I remember the people who I was having boba tea with, they were like giddy about my disgust at it. And so then they were like, a few days later, you want to go get boba tea? And I was like, I don't. I didn't get angry at them, but I was like, no, I'm all right. I'm gonna do anything but get boba tea with you people who have kind of betrayed me. So a plum pudding model is kind of like boba tea, where there's the tapioca balls or there's the pieces of plum that are kind of peppered throughout. And so you have this idea that there's electrons that are just kind of randomly distributed. There's no organization or anything to that. And behind those electrons is, well, you've got this positive space. You have these protons. Now, that's an old model, and it was ultimately disproven. So I'll just go ahead and add in here disproven model. Now, the model that currently exists, kind of as an evolution of the, or as a like next progression from the plum pudding model, was what's known as the Bohr model of an atom. And the Bohr model basically has, it's almost like a living organism cell, like a skin cell or something like that. It's got a nucleus. And that nucleus at the middle doesn't have genetic information. Um, and actually, whenever I say it, a cell's nucleus, could you give me a number in the chat if you're like, okay, yeah, I can recognize that phrase. That's not too wild. And a letter if you're like, no, it didn't take biology. Okay, cool. Um, so the idea is that, well, every living organism is made up of cells. And at the center of a cell is the nucleus that basically contains all of the important information and all the genetic information, all the DNA that you need to make, kind of make a new organism. Um, Now, when we talk about the Bohr model of an atom, we talk about a nucleus, and it doesn't have DNA because an atom doesn't have DNA, but it has subatomic particles. Subatomic particles. It's got neutrons and protons. So protons and neutrons are packed into the middle of an atom, and then outside of that are electrons. So the electrons, though, in the Bohr model, there is a little bit of an organization to that. Now, I want to give you this information on like proving or disproving the plum pudding model. So this is our plum pudding model where basically we have electrons that are scattered throughout. And there's a guy named Ernest Rutherford, E. Rutherford, who I believe was at the University of, it's not Laval, um, McGill, I think, in Quebec. And I think it was in Montreal in Quebec. And what he did was he got gold foil to represent his atoms, and he basically shot negatively charged particles at this gold foil. And he detected those negatively charged particles. And he said, well, you know what? If we've got these electrons kind of scattered throughout, then what's going to happen is some of these negatively charged particles are going to deflect off and others are going to go straight through and they're going to deflect off in a certain pattern. And based on the results of this gold foil experiment, he disproved. So I'm going to say what I want you to take away from this is Ernest Rutherford conducted a gold foil experiment that disproved the plum pudding model. Now, that's valuable information. But here we go into our subatomic particles. We talked about these last time: protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. They make up your mass. They make up the mass of an atom. Protons have a +1 charge, electrons have a -1 charge. Now, the number of protons are equal to your atomic number, which gives you the identity of an element. So I want to see your responses in the chat. Let's say I have an atom with 3 protons. The identity of that atom is lithium, Li. Now, give me a number for yes, or true/yes, and then a letter for no. If someone came along and they said, "Good news, I have a atom of lithium with 4 protons." Is that possible? Okay, well, you're right, it's impossible. This statement right here, an atom of lithium with 4 protons, that simply can't be true. Because an atom with 4 protons is not going to be lithium. Because the number of protons gives you the identity of an element. 3 protons is lithium. So if I said, oh wow, I isolated a particle or a atom, it had 3 protons and 47 neutrons and 9 electrons. Give me the symbol for that atom. And let me rephrase that. And let me ask you this instead. Is this information that I have a box around, does that matter? Add a Y for yes or an N for no into the chat. It doesn't. So, I mean, really, I could say, oh, well, it's got 912 neutrons. Does that change anything? No. Any and every atom with 3 protons is going to be an atom of lithium. That's like, you can think about that almost as a definition. So, on the exam or quiz, if you see something like Li has 3 protons, 4 neutrons, 3 electrons. If that's a true/false question, that's true. And then if I rephrased it and I said Li can have 3 protons, 2 neutrons, and 5 electrons, and that's a true/false question, that is again true. Because all that you really need to worry about is this number right here when it comes to identifying an atom. Now, we'll skip that. Instead, we're going to go on to this right here, isotopes. Okay. Has anyone ever watched the TV show The Simpsons? Great. It's great. That's all there is to it. I bring the Simpsons up because the baseball team name in Springfield is the Isotopes, which is actually the name of a minor league baseball team in Albuquerque, New Mexico. Now, here what we have, this one, far left, middle, and far right. These are all Hydrogen atoms. Okay. Let's go through and kind of profile each one of them. On the far left, I'm gonna give these lines to divide them. Tell me the number of neutrons in this model on the far left. Zero. Okay. How about in the middle? One. Perfect. Far right, number of neutrons. Two. Okay. Now answer this question for me. Are these all hydrogen atoms? Y for yes, N for no. They are. They are. The number of neutrons changes among them, and that doesn't impact whether or not they are hydrogen. Now, the number of protons in each one of them. How many protons are in each one of them? Boom, boom, boom. One proton. One proton defines this as hydrogen. A single proton is what defines an atom as or gives an atom its identity. So the number of neutrons can change, but the number of protons cannot. Now, in terms of other things that vary, we'll get into that in a little while. But isotopes are atoms with the exact same number of protons, but different number of neutrons. So if we go back here, and I were to show you this. Well, the one that I have labeled A and the one that I have labeled B, if you look where the label A is, I say lithium has 3 protons, 4 neutrons, 3 electrons. That's true. And then I've also got lithium has 3 protons, 2 neutrons, 5 electrons. These are both true statements. What is the best word? Spell it out in the chat to define these two lithium atoms, or that describes them well. They are isotopes. Perfect. These two isotopes happen to have different numbers of electrons. I'm going to go ahead and change that just so I'm only changing one variable. But 4 neutrons versus 2 neutrons, these are different isotopes. Now, what I want you to notice about these isotopes, these hydrogen isotopes, is that we've got different indicators that are different terms for them. So we've got 1H, 2H, and 3H. These have different common names. This one on the far left is the common isotope. This one in the middle has a common name of deuterium. And then on the far right is tritium. More than anything else, you'd call this hydrogen 1, hydrogen 2, hydrogen 3. I'm not expecting you to know these common names or anything like that, but what I do want you to know about is anytime you see a symbol like what you see here and a number, just know that that number on the upper left-hand corner of the symbol, that indicates the mass number. So that indicates the number of protons plus neutrons. So if we can go back to our old friend lithium, I want to see you guys respond in the chat. First of all, how many protons do we know that lithium has? 3. So if I were to write something like this, Li 12. We know that that lithium has 3 protons. How many neutrons does it have? Perfect. Perfect. Li 7. How many neutrons does that have? Perfect. I want you to be able to use that deductive reasoning to recognize a symbol like what you see here and what you see here and say, okay, well, I can reference the periodic table and I know that lithium has an atomic number of 3. So it has 3 protons. Therefore, well, 12 minus 3 is 9. This lithium isotope has 9 protons or 9 neutrons. Okay, this is going to be on one of your activities, but I think that it's a good approach to understanding atomic structure. These two things right here will go in the middle. Electrons are going to go around. Now, let's say if I were to, so this is our model for an atom. What I want you guys to do is tell me the charge of this atom. And whenever you do so, I want you to think about, okay, well, a charge can be negative or it can be positive, and charges can have different magnitudes. A charge can be +2, it can be +1, it can be +3. It could also be -3 or -4. So I'm going to write in some things here, P, 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 P. What is the charge of this that I've gotten displayed at this atom right now? Nice. You're right. Okay. Now that X, where I have those 4 protons, that's my nucleus. I'm going to add some neutrons. Now that I have those neutrons there, tell me my charge of what I've got drawn here. Still +4. You're absolutely right, because I added neutrons. Neutrons have no charge. Okay. Now, tell me my charge right here. +2. You're absolutely right. We built this up. We added our protons. We added some neutrons. Got to be honest, I added the neutrons to kind of throw a little curveball towards you. I added those neutrons, and then I added the electrons. My 4 positively charged protons and 2 negatively charged electrons gives me a charge of +2. Now, what is my atomic mass? This is a little bit tricky. What have I talked about with respect to the mass? If we go back here, we got a vote of 4 something. Okay, so mass number. So whenever I ask for atomic mass, that is thinking about, you could think about isotopes. P plus N. So 4 protons plus 5 neutrons, a mass of 9. There are 2 terms that people get mixed up from time to time: atomic number, mass number. I didn't mean to. I didn't mean to. Yeah, I I did. Okay, I did mean to. So atomic number is number of protons. Mass number is number of protons plus number of neutrons. So if I were to look at this and then look at, I think I got a periodic table in this slide deck somewhere. Let's see, where are we? Okay, slide 9. So I'm going to jump ahead. I've got 4 protons. So that gives me beryllium. So what I'm going to do is I'm going to say, well, this is Be. And then I'm going to put a number right here. What number should I put right there? Add it to the chat. Nine. That's where my mass number goes, because Now what I could do is I could say, all right, well, was that another neutron? A neutron, that's 10, that's 11. So now this is a different beryllium isotope. Can you give me a number in the chat if you follow that, or a letter in the chat if you would like another example of an isotope? Okay. So what I'm going to do is I'm going to clean the slate here. And we're going to kind of build all this up. Do the electrons not cancel two of them out? The electrons cancel out the charge of the protons, but they don't cancel out the number of protons. Okay. So here's what we'll do. What we're going to do is I'm going to jump over to the periodic table and I'm going to grab, let's say, nitrogen. Let's all look at nitrogen. Shame, nitrogen, we're looking at you. Okay, it's got two numbers on there. One of them is a whole number, and that is 7. We're going to focus on that. We'll come back to the 14.007 later on. So we know with that atomic number, because there's two numbers on any symbol. There's the atomic number and the mass number. Our atomic number is 7. Our symbol is nitrogen. Okay. Now, what I'm going to do is I'm going to write in 1, 2, 3, 4, 5, 6, 7. So here what we have right now, this is an isotope of nitrogen. If we were to detail this isotope of nitrogen, we would say N, that's our symbol, and 7. Why is it 7? Well, it's 7 because we've itemized or documented everything that's in the nucleus. And my question for you guys is, how many neutrons are in the nucleus? Add it to the chat. How many neutrons are in the nucleus of this right here? And keep in mind, we're building this up. We got 7 protons, but how many neutrons? 0. So now add a Y or an N. Is this true and representative of this atom, or this an isotope of this atom that I have an arrow pointing to? Yeah, it absolutely is. Now, what I'm going to do, because we're good there, what I'm going to do is I'm going to add a neutron. Actually, you know what? I'm going to change colors. I'm going to go with a green for the neutrons, just to make it a little bit more, or stand out a little bit. Neutrons, neutrons. Okay. Now I have my atomic symbol N. What number should I have right here as my mass number? 9. You're spot on, because I need to take into account all of my protons, which is 7, and my 2 neutrons. So I've got a 9 right here. Now I'm going to go ahead and say N, 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 N. Okay. So I'm going to cross this out just so we're kind of keeping pace with things. N is my symbol. I have 1, 2, 3, 4 neutrons, 5 neutrons, 6 neutrons, 7 neutrons, 8, 9, 10, 11. Okay, so 11 neutrons plus 7 protons. That gives me a mass number of 18. So this right here, that notation captures this atom. A symbol of N and a mass number of 18. Okay, can you give me a number in the chat if you follow? And then a letter in the chat if you don't follow. Okay. And oh, great. Sparrow, that's a great question. So naturally occurring elements, they absolutely do carry neutrons. They carry electrons and neutrons. What I like to do is I like to think about this as I'm constructing an atom from nothing. I've just got the spare parts because that has been most helpful for me and for many of my students to understand where these numbers are coming from. So then I can throw a model like this at you and you say, "Oh, okay, well, I can piece that together as opposed to looking at the symbol on the periodic table and working backwards." So natural elements, they absolutely do carry neutrons and electrons and protons for that matter. So I apologize if that was a little bit confusing, but um, yes, to answer your question. Now my question for you guys is based on this symbol right here. What is my charge of this atom or of this specific isotope? 7 plus 7. You're absolutely right. Why is it plus 7? Because we have 7 protons and 0 electrons. If I threw some electrons in, 1, 2, now we're talking plus 5. If I threw another, now we're talking, well, plus 3. So that's why I want you to, be thoughtful of, okay, electrons don't do anything to the mass. That's why I like to add my electrons at the end because this mass number, this 18, if I had 4 electrons, if I had 9 electrons, that 18 does not change because that 18 is solely from what is in the nucleus. And what is in the nucleus is my protons and my neutrons. All right. Now, we've been playing around with this a little bit, talking about our protons, neutrons, and our electrons, and coming up with our charge. That's something that I want you guys to be able to do. I want you to be able to deduce what is the charge based on the different subatomic particles that are present. Now, this symbol right here shows everything that you would kind of expect to see in a singular atom symbol. Now, what I want you to notice here, though, is, well, we've got I'm going to circle, actually, here's an idea. Give me the symbol for an atom that has 31 protons, exactly 31 protons, no more, no less. Give me the symbol for that. Add it to the chat. Ga. That's right. Gallium. Gallium has 31 protons. An atom of gallium has 31 protons. And you are spot on there. Okay. Now, if I were to, give you another example, let's say an atom with 38 protons. 38, we're looking at strontium. We are looking at the whole number as opposed to the number that has a decimal. Now, that's something that I know always is a little bit confusing. Okay, our whole number is our number of protons. So let me ask you this. How many protons does tin have? Tin has the atomic symbol of Sn. How many protons does tin have? Add it to the chat. 50. Great. Now, if we take tin as our example and work with that, I think that it's pretty. I know that I struggled with this. I was like, okay, tin SN has 50 protons. Got it. And then I know that I can look at my other number and deduce how many neutrons it has. 118.71. Okay, so that means tin has 68.7. What? Sorry, 50. 68.71 neutrons? Huh? Wait a minute. Wait a minute. Whoa, 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 whoa. 68.71 neutrons. So I can have a fraction of a neutron? That doesn't make any sense. You're right. It doesn't. What this is showing is the abundance. This number is the weighted average of different isotopes. So what this means is that there is likely a tin 119, tin 118, tin 117. These, tell me how many protons each one of these has. Add it to the chat. 50. Tin 119, 118, and 117. What are these known as? Isotopes. Perfect. Okay. Now, a fair question there is, well, how did we arrive at 118.71? Let's say hypothetically here, we've got three different isotopes. This number, this 118.71, is a representation of the atomic abundance of all of them. That would essentially what this is saying is that 85% of all of the tin isotopes are 119. And then these are numbers I'm just coming up with kind of off the cuff. 10% of them are 118 and 5% are 117. So this is taking into account all of those different isotopes and saying, okay, based on their relative amounts, this is what they are. Now, what I always like to do whenever I think about these atomic abundances is I'll say, all right, well, I like to use models and analogies to help me understand things. And I'm going to come back to that slide, but an Oreo cookie, everyone's favorite vegan dessert, consists of two wafers and one cream disk, I'll call it. Okay. Would everyone agree that that is the definition of an Oreo cookie? Add a Y or an N to the chat. I'm hoping for lots of Ys, because if somebody has something else, I don't know what that would be. Oh, I suppose you could have like chocolate covered Oreos. But here we go. This is our base definition of an Oreo cookie. Now, let's say that I got 10 Oreos and I weighed them all. You know, got a digital balance and determine the mass of all of them. Do you think that the masses are going to be the exact same? Chances are slim. Minor imperfections, like, you know, maybe some are different parts are made in different factories and plants. But let's say hypothetically that of those 10 Oreos, there were 7 of them that were 36.4 grams. 2 of them that were 32.2 grams. And then one of them was, let's say, 41.6 grams. If we wanted to come up with the average mass of an Oreo cookie, well, we couldn't just add these three numbers up and divide by 3 because there's not an equal abundance of them. Instead, what we would do is we would say, well, 36.4 times 0.7. The reason that we'd say 0.7 is because that is 70% of the Oreos have this mass. Then we would take 32.2 times 0.2, which is 20%. And then we take 41.6 times 0.1. We'd add those up. And we would come up with the average atomic mass of 36.4 times 0.7. And I'm going to write this math out because if I don't write it out, I will get lost. So 36.4 is 25.48. 32.2 times 0.2 is 6.44. 41.6 times 0.1 is 4.16. So 4.16 plus 6.44 plus 25.48 gives us 36.08. What we did was we said, well, 70% of them have this mass. So we weigh this against the whole group. We say 0.7 times 36.4. Then we say 0.2 times 32.2. And then we say 0.1 times 41.6. And we get this as our weighted mass average. So these different cookies are Oreo isotopes. They have different masses. And in order to figure out the average mass of an Oreo, this is what we had to do. Can you give me a number in the chat if you follow that, and a letter if you do not? Okay, great. So this is the sort of question where, if we took what we would do to answer this sort of, or a question that you might see related to this would be something like, what is the weighted average mass of tin? You would say 119 times 0.85 plus 118 times 0.1 plus 117 times 0.05. We'd add those numbers up and we'd get something around that 118.7 or so. And these are just rough numbers, but that's all that you need to do. You need to take the mass of one isotope and multiply it by the percent abundance and make that a fraction. Okay, how do they choose the average mass of an element if it can change consistently? It's a great question. So let me tell you this. So have you ever heard of a term, a half-life? I know that it's a video game, or it was a video game that my friends played in high school. But okay, good. A half-life is something is stable for this amount of time. And then after whatever its half-life is, basically half of it is gone. So the isotopes are actually pretty stable. Individual different isotopes are fairly stable. So what that means is that it's not really choosing and saying, oh, well, this one gains or loses a neutron. Instead, if you were to go out into your backyard or go out into the yard and, pick up some soil or something like that, you could itemize out all of the carbon that's in there and come up with a relative abundance of different isotopes of carbon. And then if you left that for 50 years, it's not going to change those different isotopes of carbon. So isotopes are pretty darn stable. Although they can gain or lose a neutron, it has to have something dramatic has to happen. There has to be something done at like an atomic level for that to happen. Now, gaining or losing electrons, on the other hand, is a different story, which is why isotopes, or sorry, gaining and losing electrons easily happens. Gaining or losing neutrons doesn't happen kind of as freely. Does that make sense? Ooh, that's a great question. So the could atomic number averages change then based on environment or region or other levels of chemicals around? That is a great question. And these numbers are representative of, they're kind of like theoretical numbers. So these are like based on different math models speculating on, or sorry, based on like, oh, all of the cadmium taken from the mountains and or the Himalayas versus all the cadmium taken from different places around the world. And based on that, this is what we believe the isotopic abundance is. So to answer the question, or to answer your question, it's pretty unlikely to change. Something pretty dramatic would have to happen in order for those to change. Could they? Potentially. Especially if you think about like, or one of the things that I always kind of am curious about is, at the center of the earth, for example, you have these like hugely dramatic nuclear reactions taking place. And when a nuclear reaction or a nuclear bomb or any sort of nuclear chemistry is taking place, you're changing the nucleus of an atom. And so there are some atoms that potentially, let me rephrase that. There are some isotopes of different atoms that exist maybe in the center of the earth that we can't really account for because of their lack of stability. Most of these numbers are based on, well, the most stable elements or the most stable isotopes. Those are going to be the most abundant, and so they kind of feed into that. So that's why I would say if there is like, let's say that there is hypothetically, just for another contribution here, a tin 126. Well, that would effectively be 0.00001%. Let's say that does exist, or that can exist under certain circumstances and under environmental conditions in the center of the earth or something like that. Well, it's 0.0001% of the overall abundance. So it's kind of it's almost a non-factor because it's so rare, basically. Does that make sense? Sorry for the lengthy, meandering response. Okay, cool. All right. What we're we are definitely interested in protons, neutrons, and electrons. Neutrons and protons, whenever you hear about uranium enrichment. So if you've ever heard the term uranium enrichment, or if you've ever heard of like centrifuges for uranium enrichment, what is being done is samples of uranium are being used to isolate uranium-238. Uranium-238 can be used for nuclear weapons because they are involved in nuclear reactions and these what is that? Fusion reactions or fission reactions. I think it's fission reactions. Enriching for a particular isotope of uranium is something that like the International Atomic Energy Agency is always curious about, as is the United Nations, as is basically every country around the world. Who's making nukes, and is that good or bad? Now, electrons, despite this interest in nuclear weapons and using centrifuges to enrich for a particular isotope, electrons determine the chemical properties of an atom. That's not to say that um, the nucleus is not important, but more times than not, what an atom does or does not do is based on the electrons that it has. So I got to close my chat, and that's going to kind of clear this up a little bit. Um, this right here is a spectral tube or a spectral tube holder. And what this is basically, you could think about it almost as a light. And within this glass chamber is hydrogen gas. You can plug this into the wall and you send an electric current through hydrogen gas with a particular, I think it's probably, I don't know if it's tungsten or aluminum or what exactly, but a metal coil that basically ignites that hydrogen gas. Maybe not ignites, but it excites that that hydrogen gas. And if you hold that, or if you look at that, you'd see, oh, cool. There's a neat little indigo color. Oh, cool. Hydrogen gas, whenever you send an electric current through it, makes an indigo color. Okay, cool. Now, if you've ever listened to Dark Side of the Moon by Pink Floyd, or if you've seen the cover for that album, the cover for that album has something known as a prism. And with that prism, you can shine light through it, and that light, that white light that goes through that prism, then distributes into all the colors of the rainbow. Okay, so white light goes through this prism that gives you all the colors of the rainbow. Can you give me a Y or an N in the chat if you follow that? A Y if you do, an N if you don't. Okay. Now, if you take this same hydrogen discharge tube that's producing this indigo color and you hold a prism up to it, well, rather than getting all the colors of the rainbow, you just get 1, 2, 3 different colors. Huh. So that indigo is these 3 colors combined. That indigo is these 3 colors that are produced, or sorry, so indigo from hydrogen gas is going to emit these 3 colors whenever you hold that indigo up to a prism. Now, the important part about this is that if we were to remove hydrogen gas and instead put something like oxygen gas in there, do you think that well, first of all, add a Y or an N, do you think that the light that's going to be emitted is going to be that same indigo color? If we change the gas from hydrogen to oxygen, add a yes or add a Y for yes or an N for no. You're right. It's not. So different element means different color. Then, whenever you produce a different color, if you hold that up to a prism, well, you're going to get not just these 3 colors. You're going to get something else. You might get 4 colors. You might get 5 colors. Now, the significance of that we see here. We see the exact same apparatus, helium, nitrogen, hydrogen, neon. We're sending these 3 gases into this chamber with an electric current sent through them. You're going to get different lights from them. If you hold that up to a prism, you're going to get a different spectrum of colors. And that's because these different substances, helium, nitrogen, hydrogen, and neon, Well, they're different at the atomic level. They have different numbers of electrons. And as a result, those electrons are going to give off, or those atoms are going to give off different energies. Okay. Now, I want to come back to that in just a moment. Here is that hydrogen gas spectra. Now, just so I want to draw a picture of a common hydrogen isotope. We've got in the middle proton. I'm just going to do P. Then we got our dashed line that our electron is on. Okay, first things first. Do you agree, add a Y to the chat, if this is a good model for a hydrogen atom? And if you disagree, or if you say that's a bad model. And if it's a bad model, based on what? Not just my artist rendering. We've got one proton, one electron. This is a hydrogen atom. Okay. Now, when we send an electric current through something, specifically when we send it through hydrogen, this hydrogen electron is basically the way that we think about it and the way that we kind of visualize it is we say that this hydrogen atom is on its lowest energy level. It starts out right here, this n equals 1. Think about this dashed line as n equals 1. You could think about it almost as the starting point for an electron, the lowest energy level. I'm going to say lowest energy level. Okay. Now, when you send an electric current through something, you're kind of electrocuting it. And this electron is going to shoot out. I'm drawing a couple more dashed lines to represent different energy levels. Okay. This electron is going to go to a super high energy level way out here. Then, so think about that as like this n equals 5 right here. So this electron gets excited. And when you get excited about something, after a little while, what happens? You know, it's like, oh man, the new Jurassic Park movie's coming out. All right, this is great, this is great. What do? Eventually, you're going to calm down. You're going to go back to where you started because, you know, the movie haven't gotten to the movie yet. You're pumped. You are geeked about it. You calm down a little bit. Yeah, you might lose control a little bit, but eventually you're going to come back down. So whenever you come back down, that energy that shot you up to this highest level, that's going to be released. And that energy that's released gets released as different wavelengths of light. Have you ever heard of like light energy? And not necessarily light energy like an Instagram influencer of like, go outside and receive the healing light energy of the sun. But if you've ever heard of like red light therapy or something like that, well, that red light therapy does do something. It is, and blue light therapy. I mean, really, there is energy associated with light. And so this is energy, or sorry, it was electrical energy that shot this electron up to this highest energy level. But then as it settles back down to where it started, that energy is going to be lost. And that energy is going to produce this light. Whenever you talk about a sample of a hydrogen or of hydrogen gas, are you talking about a single atom? No. And since you're not talking about a single atom, you're not talking about a single electron. There's an almost infinite number of these that get shot up to different levels. And when they relax, they produce different wavelengths of light. So these different wavelengths of light represent, let me rephrase that. This, different wavelengths of light represent electrons coming down from different energy levels. Now, give me a Y in the chat if you follow this statement. An N if that doesn't make any sense. Okay. So okay, fair enough. So we have these electrons in different positions, and I'm sorry, my model. Well, here, let me go back. I'll use this one. We have electrons here, 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 here. When you send energy to shoot this electron up to here, and I'm circling this one and comparing it to this one. If these two electrons get excited and go to the same energy level, where I'm putting an X. So my first question is, do you follow that these two electrons that I've got circles around have different starting points? And whenever I say starting points, I mean in proximity to the nucleus. Okay. Now, my follow-up question, do they end up in the same excitation state where this X is? Are these X's on the same energy level is kind of my question. Yeah, they both get jacked up. They're both pumped. They both go up to this level. Now, my next question is, when these two electrons that I have circles around, when they settle back down, I'm going to erase just to make it a little bit less chaotic. When these electrons settle back down to their starting point, are they going the same distance? Are they going to the same energy level? This one at the bottom is good. Go there. This one is going to go there. So another way of putting it is, how many energy levels do they cross over? So this one, let's see, there's 1, 2, 3, 4, 5, 6. So they both, well, keep track of this, both go to 6. I'm going to label them A and B. A goes from 3 to 6, then settles back to 3. B, by comparison, goes 1 to 6, then settles back to 1. Everything that I've got written on this slide so far with these three bullet points, can you give me a Y or an N, a Y if you follow that, and an N if you don't? Okay. Now, if you think about these in terms of the distances that they travel, and you think about using energy to travel a distance, do A and B travel the same distance? A goes from 6 back to 3, and B goes 6 to 1. Is that the same distance? No, it's not. Okay. Would you agree that B travels a farther distance than A? Okay. So if B is traveling a farther distance, do you think that the same amount of energy is used to travel those two different distances? You could think about it as no, you're absolutely right. They don't travel the same distance. They don't use the same energy to travel those same distances. If one is going to use more energy or release more energy, B is going to release more energy. Does everyone follow that? Okay. So if A releases, and I'm not even going to throw a number, I'll say, well, actually, I'll go 6 to 3. I'll call it A releases 3 units of energy. B releases 5 units of energy. Okay, so these are our two big points. Well, then, between A and B releasing 5 units of energy, this is more energy. And just by different energies, equals different colors. Sorry, I wrote over stuff, but can you can you give me a Y in the chat if you follow the idea that different energies mean different colors? So so the A and B would be different lights. Absolutely. Spot on. And now if you think about if you follow that logic, if you follow that A and B give different lights, both of these electrons, A and B, they both went to n equals 6, that energy level number 6. Okay? If we look at our hydrogen atom, hydrogen only has 1 electron. And of course, this is lots of different hydrogen atoms. Some of them went to n equals 5. Some of them go to n equals 4. Others go to n equals 3. So based on the energy level that something gets excited to, where I put this X, and then where it relaxes to, where I put this Y, different lights are going to be produced. So my point is, hydrogen is kind of a simple model because there's only 1 electron. It produces 3 different lights. If we think about something like magnesium, magnesium has 12 protons. An isotope of magnesium, let's say 24, isotope 24 has 12 neutrons. A neutral magnesium atom has 12 electrons. Do you think that Do you think that magnesium will produce the exact same color profile as hydrogen? Hydrogen with one electron and magnesium with 12 electrons. You're right. It's not. It's going to produce a different color profile because these 12 electrons, well, they'll go up to different levels and then they'll settle down. Then they'll go up here, settle down. And then some at an outer point will settle down. And this is all based on kind of movement of electrons. So these different colors are indicated by, or these different colors indicate electrons at different positions around an atom. Now, as an example of this, as an example of these different activities or these different electron placements, if you do what's known as a flame test, where you have a Bunsen burner or just, well, a light or a flame source, and you have different samples of different materials, they're all going to burn differently. Now, last Friday, it's possible that you saw some of this because depending on the metals that are or different materials that are in a firework, you're going to have a different color. So chances are, if you saw a green firework or green fireworks explode, you probably saw a firework or fireworks with boron or copper. If you saw something that was this brilliant red color, well, chances are it was lithium or strontium. If it was orange, chances are it was sodium or calcium or potentially iron. Now, if it was like distinctly orange, well, tell me in the chat which of these elements basically only produces orange. And you can go with the full name or the symbol if you know the symbol. And I know, I'm sorry, I'm blocking part of the screen. Calcium or sodium are going to be the best answers. Sodium is probably the best answer, though, because calcium, just at the bottom of that flame with that little bit of blue, is going to make it distinct from sodium. So people have used these flame tests as ways of determining like the purity of a sample. Um, if you are like historically, if you were in like mining or something like that, and someone was like, "Oh yes, great, we found this iron mine that we can, sorry, this area of land that has tons of iron." Okay, well, great. What we're going to do is take a sample of that and we'll use a flame test. And if we hold it over that flame, hold it over that open flame, and we see, oh, well, it kind of turns this like reddish orange with a little bit of blue. Okay, cool. That's iron. That's great. If it's purely um, purely orange, well, chances are that's sodium. So these tests were used to determine um, the identity of different materials. Now, what these are based on, these different colors that are produced, if you held a prism up to this, you're going to get different colors. And those different colors are indicating um, the different placement of electrons and where electrons get excited to and then where they settle down to. So, there we go there. Okay. Now, with respect to organization of an atom, how many electrons can go in these different kind of spheres or these different circles? Well, in the first circle, oh, great question. I believe that it does have to be a prism because a prism is the only way that I know of that you can actually kind of like get that distribution of colors. Um, so I can't think. I mean, in terms of now when it comes to mining, it's not a flame test. I'm sure that this usually what's done now is a technique called mass spectrometry, um, in which case you analyze it with different chemicals and different compounds to identify with a higher level of accuracy than looking at it with your naked eye. So in these orbitals or these circles around your nucleus where our X is, you have 2 electrons, and then this next sphere, you can have up to 8 electrons. So combining these first two levels, you can have up to 10 electrons. 2 in the first sphere, and then 8 in the second sphere. Now, with that, this is the Bohr model. And this model is like simplification. It's a simple model for where electrons are. If you've ever seen the show Breaking Bad, which I've watched like 7 episodes, and then they put a guy in a bathtub, and I kind of lost it, and I was like, not for me. Um, then you're familiar with, I think, the central Walter White's character, I think, goes on to be Heisenberg. Well, Heisenberg is a name based on the Heisenberg uncertainty principle. And that's an idea that it's at no point in time can you definitively say where an electron is. You can make kind of educated guesses and presumptions, but you would not be able to say, oh, it is this many nanometers from the nucleus, and here's exactly where every single atom is. So that it's a theory. And based on that, we have atomic theories of what an atom looks like. So all of these electrons surrounding an atom or surrounding a proton, well, this is an early model. And since then, the models have been refined over and over again, where we're getting more of a prediction as to where electrons are. And out of the interest in kind of the complexity of this is where we're going to stop right now. The send away or the take home from this is essentially this model with these orbitals. That's a good starting point. It's a good idea, but then it gets a little bit more complex than that. So I'm going to stop with this slide. We'll pick up with this slide tomorrow. This slide number is out of 25. This is slide number 17. The next few slides are not that tricky. Sorry. This slide right here is the tricky one. And it is a idea of where electrons are. And I'd rather start with this. Actually, you know what? I'm going to work through this. I'm going to stop at this slide, but I'm also going to start with this slide tomorrow. So this will make the beginning of tomorrow's class redundant, but it gets kind of abstract. I'm going to give everyone a couple of seconds. If you want to just take this on tomorrow, by all means. I hope you have a great afternoon. I'm going to continue recording this so that, if you want to revisit in like 2 hours, you're more than welcome to. So I'll give about 20 seconds and then I'll take back, or I'll continue. So if you're going to leave, have a great afternoon. If you got questions and you're going to leave, shoot me an email. I'll get back to you. Okay. So I'm going to close this right here and I'm going to clear all my drawings. When we talk about an element like, let's go with, perfect. We'll go with borium. I'm going to write this down, 107, 270.11133. Okay. So the 2 and 8, those were like the starting ideas based on all these different spectra that people came up with. The Bohr model of an atom is basically that you have one inner sphere or one ring where 2 electrons can go. And then the next ring is where 8 electrons can go. Now, So to answer your question, the 2 and 8 come from somewhere specific or just by you? It's not just by me. This is kind of the Bohr model of an atom. Now, with that in mind, if we think about something like hydrogen, simple, one electron. If we think about something like magnesium, okay, maybe not quite as simple, but you can kind of process it and figure it out a little bit because magnesium with an atomic number of Mg, well, it's got 12 electrons. Okay, so if we were to place these two, be two here, and then one, I'm just going to use X's to illustrate. 5, 6, 7, 8. Okay, so that's 10 electrons. And then if you can imagine another circle beyond this, that's where you'd put more electrons. So the Bohr model is basically you've got these rings that surround a nucleus, and it's just larger and larger circles. And that's like, okay, cool, that makes sense. When you get to something like, however, uh, borium, borium with an atomic symbol of BH has 107 protons, and therefore it has 107 electrons. When we start talking about these larger and larger circles and spheres, then it's like, well, how many orbitals are there? How many electrons are there? And is it just, do these electrons just kind of like, are they like NASCAR cars and they just go in a circle for forever? And the answer to that is no. Well, Landon, you're absolutely right. It is the number of protons, but when we talk about a neutral element, something that has no charge, the number of protons and electrons are equal to one another. So thank you for asking because that caused me to say a neutral element. Now, if we were to look at something like borium, man, placing all those electrons, we've got a ton of these circles going on. And people were doing more and more experiments and finding that that was really kind of insufficient in that it didn't really give the results. It didn't give an explanation as to what people were observing. Now, these orbitals right here are the this gave rise to the orbital model of an atom. Now, what I want you guys to do is I want you to, oh, I know this is one of the times that um the weirdness of having one monitor and using Zoom actually works to my benefit because I want you to only focus on the S orbital. Ah, dang it. Okay, so just a second. There we go. Nope, I don't know. Okay, so the S orbital. The first thing that I want you to look at is when you think about a graph uses a y-axis and an x-axis. It's two-dimensional. Now, if you were in it, I always like to think about old school Nintendo games as being two-dimensional. Now, video game technology has become much more advanced, and then you have a third dimension. This is your Z dimension. This is the part that's coming out of the screen. Okay, so when you think about a circle as being a two-dimensional object, and then someone says, "Oh, what's a three-dimensional circle?" Can you add to the chat what is a three-dimensional circle? A sphere. Perfect. Now, What I like to think about whenever I'm thinking about these orbitals is I like to think, oh, no, no, no. This right here, at the exact center, at the exact origin of me, the X, Y, and Z axes, that is where my nucleus is. My nucleus takes up basically no space whatsoever. That seems a little bit odd because that has the stuff that has all the mass, but the protons and neutrons love to pack in as much as possible. So my nucleus is where my green dot is there. Now, outside of that, I have a sphere. And I like to think about a golf ball first because I can visualize a golf ball, a tennis ball, lacrosse ball, whatever. It's 3 dimensions. And whenever it comes to, let's say, something like hydrogen, my single electron is going to be as close to the nucleus as possible. Now, whenever I think about something like helium, helium has an atomic number of 2, so it's got 2 protons. And whenever I talk about neutral helium, I've got 2 electrons. So let's imagine that we're building a helium atom. I'm going to put 1 electron right here. I'm going to draw it a little bit more clearly. 1 electron right there. That electron is going to be as close to my nucleus as possible. But remember, helium has 2 electrons. Okay, so if I put a second electron right there, my nucleus, does a nucleus have a preference on 1 electron over another? No. The nucleus is like, well, I'm positively charged. I'm looking for something that's negatively charged. Okay, there's something. I'm going to pull it in, and there's a force that attracts those two together, um, because they have opposite charges. If two things have the same charge, for instance, 2 electrons, they have identical charges. What do you know about the attraction between 2 electrons? Are they going to be attracted to one another, or are they going to repel one another? Add it to the chat. They're going to repel. You're absolutely right. Despite the nucleus attracting, well, it's going to attract kind of both of them. So these electrons are in constant motion because this electron that I'm going to put an underline by is going to be reeled in by the nucleus, which is going to force this electron outward. And so they're kind of going to be undergoing changes. So what's going to happen is this electron that I just erased is going to go super close to the nucleus. And that's going to cause this electron that's already close to the nucleus to be pushed out. And this is constantly taking place. So the electrons are both running to and running away from, or one is running to the nucleus and one is running away from it, because it's not really running away from the nucleus so much as it's running away from the other electron. Okay, so when we have something simple like helium, these 2 electrons are in constant motion, and they've got a 3-dimensional space to occupy. Now, if we talk about something like lithium, we've got 2 electrons that are going to occupy this center sphere. Then we've got a third electron that is going to occupy a space outside of there. Now, that third electron is not going to end up in this golf ball. Instead, it's going to end up in what's known as it's also known as an S subshell, but it's the way I always like to imagine is it's like the first 2 electrons are in a golf ball, and then the next 2 electrons are in a tennis ball, and the golf ball is put inside a tennis ball. So we've got 3 electrons, 2 in the golf ball, 1 in the tennis ball. Whenever we get to something like, I'm going to jump ahead here to carbon. Carbon is going to have 2 electrons, because carbon has a total of 6 electrons. 2 electrons in the golf ball. 2 electrons in the tennis ball. And then it has 2 more electrons. Those next electrons are going to be in what's known as a p subshell. So it's going to put 1 electron here, 1 electron here. Whenever we add more and more electrons, we have different places that we can put these electrons. Now, what this is ultimately going to do is make something like this right here, Kr5s2. This is a system, this orbital designation is a place or a way to describe where we place all of our electrons. When we have 107 electrons, where are they? There's going to be some in the S subshell, some in the P subshell, some in the D subshell, some in the F subshell. Now, where I want to stop right here, the last thing that I want to mention with respect to this is I want you to look at this P subshell. And I want you to look at, okay, this shape is commonly known as a dumbbell. This dumbbell can be positioned on the x-axis. Another dumbbell can be positioned on the z-axis and then another on the y-axis. They are known as the px, pz, and py. 2 electrons can fit in that px dumbbell. 2 electrons can fit in the pz dumbbell. And 2 electrons can fit in the py dumbbell. In the chat, tell me how many electrons can fit in the px, py, and z and pz combined? 6. Spot on. Now let's apply the same thing to the D subshell. 2 can go here in the dx squared minus y squared. And I'm not going to expect you to remember these indicators or anything like that. We can have 2 there. 2 there, 2, 2, 2. How many electrons can fit in the D subshell? Total. Just the D subshell, let me clarify. Ten. Okay. Last of them. So we've got the F subshell. There's 1, 2, 3, 4, 5, 6, 7 orientations of the F subshell. Each one of them can have 2 electrons. How many total electrons can fit in the F subshell? 14. Fantastic. Now, I want you to look at the periodic table. The S block here. This corresponds to the S subshell. The P block here, highlighted in green, corresponds to the P subshell. The D block corresponds to the D subshell, and the F block corresponds to the F subshell. Now, without counting, how many elements wide is the F block, which corresponds to the F subshell? Just kind of glance at it quick and then think about how many total electrons can we put in the F subshells. So we've got the F subshell has 7 different orientations. We can put a total of 14 electrons into those 7 different orientations. The F block is exactly 14 elements long or 14 elements wide. When we look at the P block, that is for 6 elements wide. How many total electrons can we put into a P subshell? 6. So for F, it's 14 because I'm talking about how wide, not the width and the height. I'm sorry about that. Okay. We are going to stop right here with this discussion. And the reason for that is this gets abstract and we're pretty much out of time. Um, I'm going to stop my share right there. What I want you guys to think about in preparation for tomorrow is nailing down or looking at that figure on the previous slide, the S subshell, all of the different subshells, and think about how many electrons can go into each one of those depictions. Because what we're going to be doing tomorrow is coming up with electron configurations. And we'll work through the periodic table and look at electron configurations for different elements. And essentially, what that means is we'll be building an atom based on the number of electrons and where those electrons are. Okay. Well, thank you guys very much for your time and involvement. I really appreciate it. We'll pick this up tomorrow where I said we would, and we will go from there. If you have any questions, you're welcome to hang around. Other than that, have a great afternoon. I'm going to stop my recording